Hello everybody, in the Programming Language Concepts course. Today's lecture is going to be on chapter number 6, and chapter number 6 can be found in the PowerPoint lecture labeled chapters 6, 7, and 8. So if you download this PowerPoint and you take a look at it, it is labeled 6, 7, and 8. If you open it up, you'll see that it is 83 slides long. Well, we're not going to do all of the 3 chapters today. I'm only going to do the first part of, this is going to be a 2-part lecture. First part of chapter 6, which is about 50 slides, but we're going to do 25 and 25. How's that? So at about 25 slides, I'll stop, and then I'll record another video for the second part, just so that the video itself is not so long. So chapter 6 is about data types. Data types, expressions, and assignment structures, statement level control structures as well. Data types are something we've talked about already. The data types come into a couple of different categories. For example, we have the primitive data types. We have the user-defined ordinal types, array types, record types, union types, set types, and pointer types. Kind of sounds like Forrest Gump with all of the different fish or the shrimp with all the different types. But this is pretty much what I'm going to cover. I'm probably going to get through record types in the first part of this video, and then the next video will cover record types to pointer types. And actually, just from an evolutionary point of view, data types are made up. They don't actually exist in the real world. They are a high-level abstraction, and this evolution started back in the Fortran days in 1956 with the integer, real, and the arrays. So if we've been programming for years, you're familiar with the concept of a data type, and this is something that's brand new. When you first start programming, when you took your first CS course, and someone taught you about data types, and you're like, "Oh, what's a data type?" Like you're supposed to know what a data type is. And interesting thing is that nobody really knows what a data type is until they take their first programming course, because they don't really exist. But in databases, they call it metadata. It's the type of data for the database column. But back in Ada days, back in 1983, Ada is actually a language that is still being used by the government. So don't think that these languages in the lecture, although it says Fortran back from 1956, Fortran is actually still being used today as well. It's being used on mainframe computers. The government uses, or the Department of Defense uses Ada as well. It was developed back in 1983. And users could create a unique type for every category of variable in the problem space. They were able to create their own types. And then we have this concept of the abstract data type. A lot of people think that came around, the ADTs came around with object orientation. They really didn't. They actually came out of Ada, where the use of the type is separated from the representation and the operations of the values of that type. Well, really, what is a data type? A data type can be defined by 2 components. And the 2 components that are part of the data type, and before I get into the issues, I just want to come back into this concept. I guess this is a good slide to stop on, I guess. The data type has 2 components to it. It has the range of values that you can assign to the type, and then it has a set of operations that can be performed on the type. For example, an int are whole numbers. You can't assign a half a number, like a 0.5 or decimal precision to an int. An int or an integer is a data type that only takes whole counting numbers. Starts with 0, goes to a particular length. In each programming language has a different length defined by that type. A lot of them use the same, but ints in C are different from ints in Java, or different in different versions of C. And so you can't always rely that the int is an int. And then just because it's called an int in one language doesn't mean it's really compatible with an int in another language either. It's a made-up concept. It's an abstraction. So it's kind of important to keep that in mind. The other component is then if we have ints, and we're going to define an int as an example, and it's going to store whole numbers, what can we do with the ints? Well, we can add them together, subtract them, multiply them, divide them, do basic math operations to them, round them, Some languages have different operations that are defined for the int. Not all programming languages support the same operations that can be performed on an int. Okay, now throughout the lecture, you're going to see slides that look like this that say design issues for all data types. Now, the word issues, a lot of people think issues is a negative thing, like, oh, we have an issue with something, or, it's an issue, it's a problem. This doesn't mean the same thing. You could take the word issue and replace it with characteristics or features. That would be a better or more appropriate way of viewing this. So the design features or design characteristics for all data types in general. Now, what you're looking at is a bunch of questions here. And you're not supposed to answer these questions, let's say, for example, for all data types in all languages. The questions would apply towards each individual implementation. So for the chapters 6, 7, and 8 that I'm going to go over here in the next couple weeks, if you continue watching the series, take off your programmer's hat and put on your language designer hat. So now you're going to develop your own programming language and you're going to invent the concept of the data type. What are some design characteristics or design features or design issues that are associated with the concept of creating the abstract data type or the abstract concept of the data type? So let's look at one of these questions. For example, the first one: what is the syntax of references to variables? Okay, so I'm going to tell you what that question actually means. I'm not going to answer the question, but I'm going to tell you what the question means. I can answer it, for example, for different languages, but in order to answer that question, I'd have to pick out a programming language to answer it for. So the syntax of the reference to variables. How are we referencing variables that are of different data types? So we've seen this already in the course. We've seen the differences between explicit and implicit data types. And we've seen them with languages like C versus Python. And now we had that at the midterm, actually. So we know that in the C language, we have explicit data types that are written by the programmer who writes the word int. And there's a word int, I-N-T, that represents the data type that we want to use, and then we follow that data type by an identifier, which is a name for the variable, like I. So if we said integer I or int I, semicolon, that would be the syntax or the reference to the variables. So that's how we're creating the syntax to reference a variable of a particular data type. Now in Python, we don't have to actually explicitly write the word int. Instead, the data types are assigned implicitly, so we just type I is equal to 5. And then the syntax of the reference to the variable I is created as a data type for a number because we gave it the value of 5. Now if we gave it the value of hello world, it would be a string. So that's an implicit form of assignment, but that is the syntax. So that's really what's asked. What in that first bullet point, that's really what the question is really talking about, is how are you going to create the syntax? So if I was going to develop my own programming language and I was going to develop syntax so that I could assign data types to variables, how am I going to have the syntax work? Now you might not know this, but there's some older languages like COBOL, and there's some other languages back there in the history of time where it didn't go data type integer, it went integer space data type. So you put in 5, and then next to 5 you wrote number. Oh, okay, so that meant that 5 was supposed to be a number. Or that hello world, and then you put next to it string. So that was our characters, to indicate that that was a character data type. So, you're kind of spoiled with C because C, if you've learned C, the pattern kind of repeats itself all over the place. In fact, just look at the differences in the syntax between C and Java. And int5 and C and int5 and Java look the same, sound the same, and pretty much do the same thing. The word int does. Java actually has, for each one of the primitives, it actually has an object data type. So there's a real integer in Java that doesn't exist in C, but I'll get to that later. That would be a Java object data type versus a primitive data type. So what operations are defined and how are they specified, which is the second component of the data type, is what range of values can the data type store? Then what operations are defined? Can you do concatenation? And if I used a concatenation and if I used a dot for concatenation, can I concatenate two characters or two strings together? Generally you can in languages that support concatenation. If I used a concatenation with 1 and 1, am I going to get 11 or am I going to get 2? Probably going to get 11. If I concatenate the number 1 and with the number 1, or with the number 2, I'm going to get 12. And so you have to specify, if you're going to write this and you're going to create your own programming language and you're going to create this concept of the data type, you actually have to specify the operations that are going to be allowed. And then I have a little definition down here. It's called a descriptor or definition. And the descriptor is the collection of attributes for the variable. And so the descriptor holds on to the range of values that can be assigned to the data type along with the operations that are allowed for that particular data type. That's really the descriptor information, and the descriptor is usually held in the same memory space as the data that is associated with the variable that's holding on to this data type. So in an implementation, a descriptor is a collection of the memory cells that store the variable attributes. So that's a little definition for you. A little new vocabulary word you may not have heard of, a descriptor. A descriptor for a variable holds on to the metadata about the variable. So it's the collection of memory cells. Well, it's a collection of information. So let's talk about primitive data types. Primitive data types are built in to the language. They're not defined by the user. They're given to the user, and they exist whether the user uses them or not. Primitives. All languages generally have primitive data types. So data types that are not defined in terms of other types are called primitive data types. They're the smallest base unit. Some of these types are merely a reflection of hardware. For example, the integer data type. I'd say about 99.9% of all languages support the integer data type. The languages that don't support an integer have a number. Let's say they call it a number, which is really an abstraction for an integer. So sometimes they almost always have an exact reflection on the hardware. So the mapping to the memory is trivial. Well, we'll see. There may also be many as different of 8 different integer types in a particular languages. And then integers are represented by a string of bits, positive or negative. In the C language, the base type is an integer, just like the slide says actually. And this does apply towards the C language. And in that particular language, if you wrote a character, that's an int. That's equal to an int. A double is 3 or 4 ints. A float is 2 or 3 ints. It's a little bit smaller. And you have increments of ints that are used as the memory allocation for each one of the variables that you're defining, for each one of the data types. So usually you have a floating point or a decimal data type. So the floating point models the real numbers, but only as approximations, which means there's no rounding to any precision. It just stores as much as the memory can hold for as many digits that you get in the particular approximate value. So if you've been new to C and you've created a float, you printed the float to the screen and you get it comes 16 characters. You put the number 12 in there and you got 12 point and you get a bunch of 16 or so characters after that. You're wondering, or maybe sometimes it's just zeros after that. You're wondering why in the world is all this crap printing to the screen? I only want 2 places or I only want 1 place. You have to specify the decimal precision that you want when you print it to the screen or when you do something with it, because it doesn't hold any preset decimal precision and it doesn't do any rounding and it can make some mathematical errors. So languages for scientific use support at least 2 floating point types, sometimes even more. And the types basically just have different levels of precision associated with how many decimal places are we going to go out to. How accurate do we want it? So it depends on how small the numbers are going to get in terms of, how many places past the decimal do we really need to keep track of. So usually the floating point is exactly like the hardware, but not always. Some languages allow accuracy specs in the code. C allows some accuracy specs, but not all. And there are floating point errors. And if you do math using floating points, you might not necessarily get the correct answer at the end. It might be slightly off compared to Java or to some other languages. C is not a math language, by the way, nor is Java, actually. And then back in the COBOL days, talking about that language again, we had this concept of decimal. So people felt like, okay, so the floating point's great. We can store, some precision to it, and we can allow the programmer to define that precision. And then people went, well, what about just supporting a decimal, like for money, where we have a 2 decimal place precision? So we have like $1.50, $1.75, $1.63, $1.15. We have 2 places past the decimal for the cents, all the way up to $1. And then we have this predetermined. So the decimal really is a floating point with built-in accuracy and built-in precision to only show 2 decimal places. And it was designed for business applications, basically so that we didn't make mathematical errors with money. Because if you're off by 0.001 or something, and you have a trillion or so transactions, it could be a couple $100,000 you might be missing, or your accuracy is not really going to be so good. So when it comes to money, people wanted more accuracy. So programming languages developed this data type, this primitive data type called the decimal. So you could store a fixed number of decimal places that's coded. And you could actually specify the precision that you wanted. And so the advantage to this is that you had some accuracy. It always rounded the same way, it truncated correctly, and it only went out to a certain level of precision depending upon what the programmer wanted to use. Now the disadvantage of this is that it took a little bit more memory than the floating point did. And also there was a limited range. It would only store, and it only stores today, and the decimal is the double, by the way. It turned into double instead of decimal in modern day languages. The double has got a limited range. You can only really get 2 decimal places out of that. And so it kind of wastes memory as well, because you have to allocate more memory so that you can hold the whole number and then do the precision on it to get it accurately down to 2 decimal places. You'd think it'd be storing less memory than a float, but because of the accuracy calculations, it needs more memory to actually store it out to do the rounding correctly. So it does take up a little bit more memory. The double takes up more memory than the float. But in modern day computers, do we really care? We have a lot of memory right now, so it's not really a big problem. If you were working with an embedded system and you had a limited amount of memory to work with, you might want to consider using the float instead of the double. The decimal also became a primitive data type for COBOL, as I mentioned before, for business data processing. So they store very much like the character sets using a binary code for decimal digits to BCD code. So yeah, they store it as a character set almost. Now we have the Boolean. And if you haven't noticed, this chapter is going to go through a ton of different primitive data types and the logic behind why they were invented. So the C language, believe it or not, doesn't actually support a Boolean. Why? Because you can use a type define for an int and have it 0 or 1 and make it true or false. So some languages support the Boolean, some don't. The original thought was if you could do it, if you could create the data type using other data types, then why do we need to create a new data type for this? And I guess the C people took more of a minimalist approach to it and said, well, and Boolean could be 0 or 1, and if it can be, then the original design said, why don't we just use an int and make it 0 or 1? We don't need a Boolean. So it was first introduced in Algor 60. Most all general purpose languages today, most of them have them. Java has them. And C++ actually has the Boolean. C never actually had it. Well, C never had a string either. If you think about it, what modern day language doesn't have a string? Well, C. C++ added the string with the string class, string.h. But that's the weirdest thing about learning C, is that there's no string. And you think, well, there's no Boolean either. You think, well, why in the world did the language leave that out? They just never thought you needed it, because you can implement a string like a character array. So the advantage of the Boolean is that it is readable. We can put true and false. It's it can be implemented using an enumeration or an int, but to actually have it makes it a little bit clearer. It's a little bit more automated. So it's a little bit more modern way of doing it. Most languages also support the character type. C actually never really supported the character type either, believe it or not. But there was an association, and the character to this day is still implemented like an int. So you could take one character and add it to another character and get a new character out of it. Because if you use 128 character set with the ASCII code, if you take a character and you typecast it to a number, or just print it to the well, if you print a character to the screen, you're going to get the character. If you print it as a number, you're going to get the ASCII equivalent number. So the ASCII 128 had different characters from 0 to 127, and they're supported in a lookup table. So really the character is a number. So the character data is stored in computers in numeric coding, either 0 through 127. You put I can't remember what the 0 is, but it's probably A or something, in there. And then the lookup coding, a 16-bit character set named Unicode, looked it up and said, well, okay, 0 is A, and 1 is B, and 2 is C, which I don't think it is actually, but it's a very similar lookup. And then you associated a number with a character. So some languages like C say, well, if they're just numbers, why don't we just put the number in there? But, they did add a character to it, which was good, because it's nice and easy, because who's going to remember the number associated with a character when you can just put a character in there? So character string types. So really a string is nothing more than one character put together, 2 or more characters, and you get a string, which is kind of an interesting concept. It's one in which the values consist of sequences of characters. And then we go back to this design issue, which I, just to reiterate the point one more time, it's more like a consideration or an implementation detail. How are you going to design it? And the first question is are you going to make it a primitive type, or is it just going to be some kind of special type of an array? If you look at C++ as an example, it's okay. So first of all, the character string was never a primitive at all. It's still not a primitive in that language. It is a primitive in Java, but it is not a primitive in C or C++. But in C, it was implemented in a character array or a character pointer. In C++, they took the character array and they turned it in, and they implemented it, housed it around a string class. So you have string.h, which is an object that represents a character array. And if you're familiar with the string, you can use it just like a character array. It's interchangeable. And so, in Java, when Java came out, Java, if you look at the syntax and you look at the language itself, it's nothing more than an upgraded version of C++. The syntax is practically the same, and the implementation is a much better version than C++. And if you want to think about it, Microsoft went back and said, okay, let's make C#. C# is C++ with Java. So C# is sort of like Java and C++ put together, which came after Java, and Java came after C++. So it was kind of like, instead of improving C++, they just made a new language, which, I don't know. I would have improved C++. And C++ has been improved over the years, but the core concept of C++ has never changed. So it certainly does not operate like Java does. And Java is a much smoother language that has things that we're missing from C++, like the string as a built-in primitive data type. So the second question here on the design issues says, what is the length of objects? Are they going to be static or dynamic? We all know that C and C++ has static length arrays, and static length strings, which is kind of interesting. But actually C++ has what they call a limited dynamic, which it says, the string can only be so long because we have to create an array, because we're going to use an array. So we know that an array is a static concept. We build an array at the beginning of the program, and we give it like 50 items or 40 items, and it doesn't grow. This is in the language of C, C++, and Java, not Python, but C, C++, and Java. They support static arrays and static strings. And Python supports dynamic arrays, dynamic strings. Okay, because C++, let's just talk about C++ and C. At the beginning of the program, even if you use the string class, you're going to create an array. The array by default is a static component, static construct. So if I make a static array and I give it 2,000 characters, which it's kind of large, it really only has 64 or something like that. I don't know. It's under 100, I think. Says that the limit of this array length, you can only go up to 100. So it's static, but we're going to create it dynamically because we're going to allow the user to put in 0 through 100 or 0 through 64 characters. So that's why they call it limited dynamic, because you can store in the string any size string that you want, but there's a limit. It goes up to the size of the array. It's kind of like how, young programmers or new programmers, they're trying to make an array and they don't know how many items they have, so they make an array that's huge. They go, let me just make an array with 200 items and I'm going to put 5 of them in there. I'm only going to use the first 5. But they have an array structure that they over-allocated for. So that's one of the problems with C++ is that string will always take up more memory than needed because it's over-allocated. It's over-allocated because it's going to support the maximum size. Every time you create a string variable with that string data type, you're going to get the maximum size available for that data type, whether you use it or not, which is kind of weird. But that's how they support a dynamic length with that string. And so for most strings, you want to support a dynamic length. And I'm still talking about number 2 here on the design issues, is the length of the object static or dynamic. Usually most modern day languages, they want to do dynamic, but how are they going to do it if they're going to do a static construct for it, which is what I was talking about with C++. Now, Java does a dynamic one. In fact, it will only store the length of the string that was assigned to the variable. However, there's an allocation and a deallocation that occurs each time you change the value because it needs to recreate the array that's going to hold on to those characters. So it's kind of an interesting way, and I'll get into that in a few minutes in some slides coming up. But I want to move on to the operations right now. What operations can you do on the string? Well, you can assign one string to another, usually. You can do a comparison. Is one string equal to another? Is it larger than, greater than? Concatenate them. Maybe say, is there a substring? Is there a string inside of this other string? Maybe do some pattern matching on the string, depending upon what you're going to do. So here's some examples about how the string has been implemented. I've kind of gone through a little bit with the C and the C++ and Java, but here's a Pascal. So Pascal was a procedural programming language, not really used that much anymore, but they started out with this not a primitive. There was an assignment and a comparison only, and they called it a packed array, which means you created an array and you populated it with the characters, and you only made the array the size of the characters that were assigned to it. Now, the thought for C and C++, and the reason why Pascal shows up on the slide, even though the language isn't really used anymore, is that it was the predecessor towards the C and the C++ implementation. They kind of copied Pascal, and they went, oh, okay. So we have Fortran 77, Fortran 9. Fortran is still being used today, by the way. Snowball, which is the scientific version of COBOL. COBOL was the business language. BASIC, we still got Visual Basic out there. It was somewhat of a primitive, but it was implemented in the language a little differently. Assignment, comparisons, concatenations were supported. They did some pattern matching. So C and C++ sort of took the Pascal version that kind of got incorporated, and Ada also followed the same line, where it's not a primitive, but you can create an object. And so the string.h, and this is really C++, not really C, because we don't have string.h actually in C. But C++, if we look at that language, we have the string.h class, which supported the string copy, string length, string compare, supported concatenation, substring references were supported in Ada. Ada does a little bit more than C++. When in Ada, that is that Department of Defense, the DoD language. Ada, if you're going to work for the government, you're going to do government contract work, you're going to learn Ada. And you probably won't learn that until after you graduate. And don't learn it unless you have to use it. It's not a friendly language, in my opinion. But it is the language the government likes. Why? It's very safe, actually. It doesn't have as many problems as C or C++. The government will not use C or C++ or Java, for that matter, in any government contract. They will always use Ada. And this is current as of 2020. I don't know. It might change in the years to come. Who knows? And then there's Java. Strings are supported as primitive types, but the string class has the string constant strings. The string buffer class has the changeable strings. If you haven't noticed, Java does a lot more with buffering versus non-buffering, and it has different forms of strings, and it really improved the quality of the C++ string.h. So Java was an improvement on that, as I mentioned earlier. It's kind of like a rewrite of C++ with better features. Okay, so here's the string length options I was talking about before, and I mentioned it was going to come up again in another slide. So what options do we have when we consider the string length? So there's several different design choices regarding the length of the string. We have the static length. So think of static length as a regular old array that you would create. If you're going to create an array, then you got a static length because arrays are static length, which means if I say I want 15 characters, then I have 15 characters. I'm not supposed to write to 16 and 17 characters. I'm supposed to stop at 15. So the length, by definition, a static length. The length is specified at the declaration time. Ada, C, in the beginning, C did this. Fortran, Pascal, they all use the static length. And the static length strings are always full because we only make the string as long as the number of characters that were assigned to it. So we say that the length is equal to 15, and it's going to be a character, and then we're going to call the variable name in this particular case. And remember, before I said that when you define these variables, that the syntax for defining them is not always the same as what we see in the pattern that's commonly used with C and Java, or C++ and Java. But that's in Fortran, that's actually how you would create a variable called name. The length is going to be equal to 15, and it's going to be holding characters, which means it turns it into a string of 15 characters. Okay, that's static. The length is specified at the declaration time. So whether you do it in an array, whether you do it in this kind of format, it's static. Limited dynamic length. It means that's the limited part. The limited part says there's a maximum. Strings can store any number of characters from 0 to some maximum number specified by the variable declaration. C++, as I mentioned before, uses a limited dynamic length. There is a maximum length. Now, what that is depends on the implementer of the language. You're like, I thought C and C++ were just C and C++. Well, they are and they aren't. Microsoft Visual C++ and Microsoft C++ has a different length than the GNU C++ or GCC C++, G++ or GCC C. They all have different lengths. They're similar, but they're very different. The actual length is indicated by a null character at the end. There is a maximum length, though, and it's generally the length of a line, and no one ever meets the maximum. Some of them try to trim it down a little bit, like UC Linux C will trim it down to make it a small string, but I think Visual C++ actually has the largest string size. But that string size is definitely per the language implementer. And then we have on the bottom, we have dynamic. Well, there's JavaScript. You could also add Java to this. Perl, Snowball. Provides a maximum flexibility, but requires the overhead of the dynamic storage allocation and deallocation. Java and Python both fall into the dynamic category as well. Python does all variables in all data type lengths and characteristics are all 100% dynamic, and Java is like 99% dynamic on everything. There's a few exceptions, but for the most part, they're dynamic. So the string is dynamic in Java as well as JavaScript, which are two different languages, by the way, and Perl. Perl is actually used a lot today. It's used a lot in transcoding and in devices like the Roku or the Apple TV or the Chromecast. Perl is a Unix scripting language that's used to do the transcoding for the data streams. So it's a scripting translation language that really good for streaming applications. That language uses a dynamic string length. And so what do we mean by that is that however characters we have and whatever we're assigning to the string is what we're going to create. And we're not going to create any more than that. We're just going to create one of the length of what we need. And then if the string changes, it grows, gets bigger, or it gets smaller, then we deallocate and then reallocate. So we remove the memory and then we create a new string at a different location in the memory and we recreate it. So there's a overhead in the compiler to have to deallocate and then reallocate because the string's not going to fit in the memory that we had for the previous one. I mean, it might if it's smaller string, but we don't know if the user is going to assign a smaller or a larger string, and so we require a deallocation and then a reallocation every time the variable value changes. So that's a lot of processing and a lot of memory evaluation. So the evaluation of all of these different choices, if you do support a string, well, it does aid in writability. You just write the word string, and you don't have to create a character array or a character pointer. As primitive type with a static length, they're inexpensive to provide. Well, yeah, it's pretty easy to do it. I mean, it means by inexpensive, it means there's not as much work. We can create a primitive out of it. It works quite well. It does have a static length, but it's it's equivalent to an array. Same issues. Dynamic length is nice, but it really is it worth the expense? And the expense we're talking about here in both of these two cases is the allocation and the deallocation of the memory. So dynamic is nice, but do we really want to deallocate and reallocate every time we change a value to a string? It's going to make our program run like a snail because of the expense of the memory allocation. In terms of its implementation, the static length has a compiler time descriptor. We need to know how many characters are in there. Either we put a null character at the end or we count them up and put it in the descriptor. The limited dynamic length may need a runtime descriptor for the length, but not the C or C++. They don't actually have one because they just put a maximum in there. C uses that null character, so we know when we hit the end, if the end is before the end. So if we make a string, we make it 2,000 characters long, but we only put 100 in there. When we put a null character at 100, then we don't have to waste our time going through the rest of it because we know it's empty. So the dynamic length, you need a runtime descriptor for it. The allocation, the deallocation is the biggest implementation problem. Just a little note at the end there, letting you know that. So yeah, dynamic, supported in most languages, not the easiest to implement. Not the easiest to do because it wastes some time in processing. So here's our implementation for our static length. Talking about that descriptor, the static length. If you think about it, when you write a static array, you have to keep track of, array 15. After you define it at the top of the code, let's say an array with 15 integers in it, how do you know there's 15 in there? Well, that gets stored in the descriptor. Now, it's not really checked in C or C++, but it's still stored. So the static length here, we have this thing called a compile time descriptor. This is the name of the type, the length in characters, and the address of the first character. So you do know that the string holds the memory address of the string is the memory address of the first character of the string. So we have the static string with the length, and we have the address. This is the descriptor, which is the information stored about the variable that's stored at the memory address along with the string. And this is just going to give us the memory address of the starting of it and what's the offset. So limited dynamic length, may need a runtime descriptor for the length. It's not used in C or C++ because C or C++ doesn't check the length, which means you could write past the length and not have a problem at all. It's kind of like, test it out with an array. Arrays don't use compile time descriptors either. So if I create an array of 15 elements, I can write in the 20 and 25th element that really doesn't exist, but the compiler will go ahead and let me do it because we don't have a descriptor for that. So in the limited dynamic string, the limited dynamic requires a runtime descriptor to store both the maximum length and the current length because we're going to put a limit on it. And so the limited dynamic is going to have a maximum. So you're going to need to put something at the end, like maybe not a character, but some sort of indicator. So you need a runtime descriptor. Only the current length is stored for that one in the dynamic because all we need to know is how big is it. So the allocation and the deallocation is the biggest implementation problem. As mentioned before, there's two possible approaches to doing this. You could do a linked list or you can use adjacent storage, which is similar to the array. So in the limited dynamic string, you got to keep track of the length because you're not going to fill up all the space that you're allocating. In the dynamic length, you're just going to allocate what you need. And so that one, you got to figure out, how am I going to make it efficient? I can make it a linked list or I can do it in an implementation of an array. Java actually does a linked list implementation, which is actually kind of interesting. But it is definitely a complicated implementation. Now we have the ordinal types, or the user-defined data types. An ordinal type is one in which the range of possible values can be easily associated with a set of positive integers. So the enumeration is the ordinal type that most people are familiar with. One in which the user enumerates all the possible values, which are symbolic constants. So some of you may not have heard about the enumeration. It was supported in C, and then as of Java 5 and above, they added the enumeration to their language as well, and they implemented it exactly the same way as they did in C. And in there, what you've got is, the word enum, E-N-U-M, space, and then let's say colors. And in the colors enum, we're going to add red, white, and blue. And then red is really 0, white is really 1, and blue is really 2. So instead of saying colors is equal to 1, we say colors is equal to white. So it adds a symbolic constant where red is 0, white is 1, and 2 is blue. We don't have to remember which one's blue. It's 2. We can just write blue. So it made it easier for the programmer to assign colors, let's say for in this particular case, instead of having to remember numbers. It's kind of like the enumeration of the states. well, actually the states. We don't know what's the 52 states or whatever. Who's state number 13? I don't know. Or let's just say, I meant to actually say months of the year. People go, 4, 5, 6, 7. I remember 1, that's January. And usually I have to, when it comes down to 8 is August, so that's an easy one. 7 is July. 6 is June. But who's going to really, we kind of use that interchangeably, but that's called an enumeration. So instead of saying 1, we say January, 2 is February, 3 is March. We are enumerating named constants, January, February, March, as words instead of numbers. That is an enumeration data type in a nutshell. So design issues or considerations associated with enumerations. Should the symbolic constant be allowed in more than one type definition? So if I make a colors enumeration and I have red, white, and blue in there, can I make my colors 2 or something? Make another one and put the same values in there? Most languages don't allow you to do that. You can only use the named constants one time, which is an interesting issue. Some examples of the enumeration in Pascal: you could not reuse the constants. They were used as an array subscript for variables. There were case selectors. No import or output could be compared. They changed that with C or C++ a bit. It's very similar to Pascal. In fact, C, the language of C there's a lot of Pascal inside of C. So they kind of copied that. You couldn't reuse the constant values, but you could do input and output as integers. I could say, if I had colors, I could say colors is equal to 1 instead of saying color is equal to white. If I had a color variable that it was the data type enumeration colors. So yeah, I can interchange the numbers with the named constants. Now the slide here says that Java does not include an enumeration type, but can be implemented in a nice class. That changed with Java 5. So I don't know, I guess it's been about 10 years since it's been out. Probably should update the slide. But yeah, Java does support the enumeration, and it does it very similar to C, C++, because it pretty much copied it. People complain, they say, well, how come we can't do an enumeration in Java? And so they added it. So enumeration types provide advantages in both the aid of readability and the aid of reliability. Now, if I asked you a question like us, say on a final exam or something like that, it said, provide, 2 evaluation criteria, or, what are some advantages of using enumerations in a programming language of your choice, or something of that nature. And you said it aided in readability or it aided in reliability, you would actually get the question wrong because you're really not saying anything. So you need to explain why. For example, if I say aid in readability, you'd have to explain that in a little bit more detail. Say something like, an enumeration allows you to remember the name like June, July, or August instead of 6, 7, or 8. So it adds a more meaningful English, which makes it more readable. So if I see June, I'm knowing it's June. If I see 6, I don't know. When I read into number 6, is it really June? No need to code a color as a number in this particular case. So if I, what is the color 16? I have no idea, actually. There's an RGB color set with hexadecimals, with red, green, and blue. I have no idea what those numbers are. I have to go online and look them up. I'm not going to memorize 2,000 or so ASCII codes to know which colors are associated with the RGB number sets. Although I can remember 000000 or 111111, but that's about it. So yeah, readability. Reliability, compiler can check operations and ranges of values. Yeah, if I say my colors are red, white, and blue, and I try to assign the color cyan or purple, compiler can come back and say, nope, sorry, that's not a valid number. That's not a valid color. I pick another color. because it can actually check because you have some predefined numbers. Now, if I just, it's kind of like if I use an int, and you can implement a Boolean, believe it or not, by using an enumeration. So you can create an enum, called it bool or Boolean, and have two, true and false, where you have a 0 and a 1. I guess that would be false and true, and then it could check. So if I said, created a variable, my Boolean, and it was a data type bool or Boolean, whatever I called the enumeration, and I assigned it tree, it is going to come back and say, no, I'm sorry. The numbers that you can assign it to are 0, 1, or true or false. Tree doesn't belong here. So that's what it means by reliability. You can actually type check the number that or the word that you're assigning to the variable to make sure that it's actually part of their range of values that's acceptable. So we also have this concept of subrange types. Subrange types are types that fit inside of other types. So it's like, that's great. An ordered contiguous subsequence of ordinal types. I don't know what that means. Okay, let me give you a nutshell for this one here. We have this concept of the integer, right? And most of you have probably heard of longs and shorts. Well, a short and a long, or a signed and an unsigned number, are all subtypes of int. They're all subtypes of integer. So an integer is like 0 to some maximum length. The short is 0 to about halfway in there. The long is about the halfway point to the rest, to the end of it. The signs are the ones that have the 0, have the plus or the minus. The unsigned, we don't care. We're going to drop that information out of there. We don't know if it's a negative or a positive number. Those are all subrange types. So in Pascal, we have the subrange types that behave as their parent types and can be used as variables of the array indices. Well, you'd think that C or C++ would have taken that on, but C and C++ treats the subranges as separate types. If I make a short, and I make a long, and I make an int, and I try to use them together, I'm going to get a type mismatch error. In Pascal, you'd never get that type mismatch error, but in C and C++, it's going to say, nope, sorry, you're trying to take an int and a short and add them together. You can't do that. It's like, well, the short is an int. It's a subrange of the int. Nope, sorry, not allowed. So the C did not follow the Pascal on that one. Ada had the subtypes that are not new types. They're just constrained existing types. So they are compatible. And they can be used as in the Pascal. Plus they are also plus case constants. Well, yes. So subrange type of index is integer, ranges 1 to 1000. Whatever was in there, whatever position is in there, as long as it's in the index of what's acceptable, is compatible. So then all operations defined for the parent type are also defined for the subtype, except for assignments of values out of the ranges, which is true for subranges. If I have a long, I'm not supposed to give it a short value. If I have a short, I can't give it a long value. And ints will take both shorts and longs. So when it comes to the implementation of the user-defined ordinal types, the enumeration types are implemented by associating a non-negative integer value with each symbolic constant in that type. So 0, 1, 2, 3, 4. The subrange types are the parent types with the code inserted by the compiler to restrict the assignment to the subrange variables. So the subranges say, well, if you're going to say it's a short, it can only go from 0 to this number here. I don't know what the number is actually, but there's a limit on it. And if it's a long, then it has to start here at this maximum length and go to another maximum length. So yeah, subranges are more specific when it comes to it. Now the slide is missing the C++ implementation. C and C++, as well as Java, do not support subrange types. They're all different types. They, instead of having a subrange, they just said, you know what? A short is different from a long, which is different from an int, which is different from a double, which is different from a float, yada, yada, yada. Even though the same numbers might fall into each one of these little categories, they're all going to be different types, and we're not all going to treat them the same, and none of them are subranges. So Yeah, we do have a short, we do have a long, we have a sign, we have an unsigned, but we don't necessarily have any association with them. They are all basically separate types. So now C and C++ does support the array. I've been talking about arrays so far, so arrays are pretty interesting. So the array is an aggregate of homogeneous data elements. We know that already. And they're identified by a position in the aggregate, usually by an index. So you specify the elements of an index by the name or the index subscript is in relationship to the first one. So we have index 0, 1, 2, 3. And when you first learned how to program, the first thing you tackled was this concept of the array. And so I can say I can take 5 ints, so I can stick them all together into one int variable, call it an array. And then I have the subscripts 0, 1, 2, 3, 4 to represent the 5 numbers. And the biggest thing you kind of came out with was, well, how come we're starting the index out with 0 instead of 1? Some languages start with 0, some of them start with 1. C, actually, most languages start with 0 for some reason. But yeah, that's the array. So what are some design considerations associated with the array? Well, what types are legal for the subscripts? So we have looked at the Python programming language, and we know that in Python we can create a list or a dictionary or an array or a tuple or one of these aggregate data types. And that's another thing to kind of keep in mind here. The array is the aggregate, and the array as an aggregate, in some languages they only have the array. And some, if you're new at programming, you associate that with a list. And the list is ordered, and the ordered list is by its index values. Well, some languages like Python have more than just the list. The array actually isn't a primitive in Python. It's in a separate library you have to add in. It's a sys library. The list is a primitive, which is weird. The dictionary is a primitive. But we can stick any types we want. I'm talking about number 1 up here, what types are legal for the subscripts. We can mix and match and put any type we want in the list or in the array. We could put a float, a double, a character, a string, another array, another list, a dictionary, anything we want in there. Other languages like C and C++, as well as Java, require all of the elements to be the same data type. So the types that are legal for the subscripts are all the same data type, and we have to specify what it is statically. Are subscripting expressions in the elements referenced by, or are they range checked? References, are they range checked? Well, in C and C++ and Java, they are not, I shouldn't say Java. C and C++, they're not range checked. So if I create an array of 5 ints, I can write to number 6. I can read from number 6 or number 7 or number 8. There's no guarantee that the compiler is even going to know there's 5 items in there. So there's the range checking would be ranging if I only said I had 5 items, am I only putting 5 items in? Java does some limited range checking, and you'll get a message if you try to write past the bounds of the array. The compiler will come back and tell you a warning message. I really think it should be an error message, but the warning message will come back and say, attempting to write past the bounds of an array, maybe not a safe operation. Usually not a safe operation because you're writing into somebody else's memory, because the memory doesn't belong to the array that you're writing to or you're reading from. So are the subscripting expressions and elements references, are they range checked? Number 2 is kind of an interesting thing. In Python, they are range checked. So if I say I have 5 ints and I ask for number 6, Python's going to come back and say there is no 6th element. There's only 5. It's not going to tell you that, but the compiler is going to figure out that there's no 6th element. And so it'll come back with an error message, which means it's checking it. So that's why sometimes people say that C and C++ don't have strong typing, because not all of the arrays are not type checked. Arrays are never type checked. They're never range checked. You can pass an array to a function, and it only has 5 items in there, but you can pretend it has 15 items, and it works. Well, I don't know, probably cause an error message or two to happen at runtime, but it will compile and run just fine until that random error comes up, because you are writing past the range. So yeah, some languages allow you to do that. They call that an unsafe operation. But C and C++ do not do any range checking on arrays, which makes it a weakly typed language. Python is a more strongly typed language because it does range check. So, when are the subscript ranges bound? In C or C++, they're bound statically. You define it at the beginning when you declare the variable, the array variable, and you say, give me 5, integers. Give me 10 integers. In Python, they're done dynamically. So the difference here is when is statically or dynamically, by the way. Whenever you see when, it's static or dynamic is really what it's asking you. So some languages do them statically, some languages do them dynamically. If I assign 5 elements to a dictionary in Python, then the subscript ranges are bound at the assignment expression. When does the allocation take place? In C, it's allocated whether you're using it or not. If I create an array of 50 elements, because I don't know how many I'm going to use, then I'm going to allocate an array with 50 spaces in it for hold 50 elements, whether I use them or not. In Python, I'm not going to do that because I'm not going to allocate 50. I'm not going to use 50. When I do the assignment, if I only give it 5, I'm only going to allocate 5 spaces. In Java, I'm going to allocate it the same as Python, only 5 spaces if I'm only using 5. But I'm going to have to deallocate and reallocate every time I change it. So the allocation takes place statically in C or C++. It doesn't ever reallocate. So if you can only create it one time and you can only allocate it one time, then you're kind of stuck. It's not as flexible. So what's the maximum number of subscripts that are allowed in arrays? Well, that's an interesting question. Maximum number of subscripts. Some languages put a limit on it, some of them don't. In some cases, you can write, an array as big as you want. C or C++ does have a limit. Java does not have a maximum number of subscripts. Python does not have a maximum number of subscripts. But C and C++ do, and don't quote me on that. I think it's 64,000 something. It's a really big number. Nobody ever exceeds it. In some languages, implementations like Microsoft versus GNU or GCC has different limitations. Can array objects be initialized? Most languages, they can. It's like when you create an instance of an object. You did this in the midterm, actually. No, actually, you did not do this. In a programming class, you generally do this. You would you have to create an array of objects, usually at one point or another. And you can realize that you can initialize them when you create the array, and you can add already instances of objects to an array as long as the array is of the object data type that is being used. Indexing is the mapping from the indices to the elements. Some languages like Python support the map. The map here is the array with the array name with the array index value as an element. The map is sort of like the dictionary with a key value combination. Fortran, PL, Ada uses parentheses. Most other languages use brackets. It's been a while since you've done an array in C. You'll notice the brackets. So Python uses brackets, parentheses, and things for different types of aggregates, depending upon if you're creating a dictionary, a list, array, a map, depending upon what it is you're creating. For the subscript types, these are some examples. Fortran, C, C++, Java, they only have integers only for the subscript types, which means the subscripts themselves, the values are 0, 1, 2, 3. You can't have like a double in there. These are not the values you're holding. These are the types for the subscripts. It's the regular counting numbers. Most of modern day languages use ints. So the ints start out 0, 1, 2, 3. Those are the subscript types. Pascal had any ordinal type, integer, floats, enumerations. Ada had integers or enumerations. Some languages, the lower bound of the subscript was fixed, which it is. C, C++, and Java always start out with 0. It is not fixed, by the way, in Python. You can actually start your arrays out with 1. Your elements can actually start with the number 1 instead of 0. Most other languages, it needs to be specified by the programmer. Like Python, you specify what your starting number is going to be. If you don't specify it, it turns into 0. So you may not notice that so far. If you've played around with arrays in Python, you may have already been just assuming it started with 0 and you were just using the 0 element, which is highly possible. In terms of the number of subscripts, Fortran allowed there to be 3. Fortran 77 had up to 7. C, C++, Java just allows just 1, but elements can be arrays themselves. So you can stick an array inside of an array. These are the number of subscripts. So you have 1 item, and they're integer items, or they're integer subscripts. So you have 1 item for 0, 1 item for 1, but you can stick an array inside of an array, so which makes a double array or a triple array. So you have rows and columns and sheets. So yeah, you can nest them together. In terms of the array initialization, usually just a list of values that are put in the array in the order in which the array elements are going to be stored in memory. So the initializations are done in a couple of different ways, but it's basically the same as assigning values to variables. So some examples of Fortran uses data statement to initialize it. C and C++, you can put the values in brackets, or you can let the compiler do it for you. So, integer stuff. And if you put in 2, 4, 6, and 8, it'll size this to 4 because you have 4 elements. So I'm not going to go through, you're never going to program in Ada throughout the rest of this course, or Pascal or modular, so I won't worry about showing you the syntax for that. But some languages don't allow the initialization in the declaration section of the program. They have to be initialized somewhere prior to the program start, statically. So slices. You saw from the second programming assignment with Python that Python supports slices. C, C++, Java do not support the concept of the slice. The slice is the subpiece. So a slice is some substructure of the array. So less than, not a new data type in itself. It's just a subpiece of an existing data type. Nothing more than a referencing mechanism. So we have the Fortran, we have the Ada. You can also add Python to the list where we want, element 5 to element number 15. It would be a slice. So kind of like a slice of pizza. You got your slices. So implementation of the array, the access is usually from a row column perspective. This is very similar. This is the Fortran, but this is very similar to C and C++, where you almost have like a grid where you have the location of I, j in kind of a matrix kind of format. Basically rows and columns. And so you can get the first row, the second column to get the index values if you're doing, let's say, a two-dimensional array. So we also have the concept of the associative array. Associative arrays are not part of C or C++, but they are part of Python. And we do have them in the map and also in the tree map in Java as a supported library. So the associative array is an unordered collection of data. So we have the index values equal to a key, and we have a value that's associated with each one of the keys. So the indexed array, or the list, is generally an ordered list, ordered index, where we have index values, subscripts, 0, 1, 2, 3. We call them arrays, or we call them a list. The associative array is sort of like the map or the dictionary, where we have a key and a value that's associated. So we have color, blue, interior, red, exterior, white, temperature, hot, where we have a key. Instead of a 0, 1, 2, 3, we have a constant value key with a value. So just think of the dictionary that you learned in Python, and then you've got the associative array. So some design considerations or design issues associated with the associative array. What is the form of the reference to the elements? Can we get at the elements using the keys? Can we get at them using the values, or both? Well, actually, it's both in Python. C++ doesn't support it, so we don't really have that. Java, you can get at both, actually, as well. Is the size static or dynamic? Most languages that support this make them dynamic. How are you going to limit the size of a dictionary? So if you're going to actually implement this with a key and a value combination, you're really going to put it together. Even Java has it dynamic. Most languages that implement the associative array do it dynamically. Another language that really does a nice associative array is actually PHP, which is a scripting language for websites. PHP and Perl. In fact, most of the associative arrays come from Perl. The PHP one, though, however, works really well with the tuple, creates a tuple. The tuple is sort of like a row in a database. Actually, tuple is means data. It means row. It's another word for row. In relational database concepts, the rows had columns in them, very similar to an array, two-dimensional array, or three-dimensional, actually, for that matter. And the tuples would associate the column names with the values that were inside of the columns. So PHP supports the tuple. Actually, believe it or not, Python supports the tuple as a tuple. The difference between the tuple and the list is that the tuple is not mutable. The list is immutable. And the tuple can have a associative array values where you've got a first name, last name, date of birth, and you have values that are associated with each one of those keys, which was something that you'd come out of a relational database table. So if you ever do any web programming in Perl or in PHP and you connect to a database, you'll get familiar with the tuple. And you can do the same thing in Python, by the way. So associative arrays are supported by the standard class libraries in Java, but the main languages that use them and support them are Perl, and I would add PHP, and I would add Python to that list as well. I'm talking about the last bullet point here. Perl was the one that started out with it. And remember, Perl is the language that's used for a lot of streaming applications these days. So it's a very relevant language these days. So here's the structure and the operation in Perl. They called them hashes. So in Perl, the associative arrays are often called hashes. And the names begin with that. Well, Perl is this funny language, actually. Instead of data types that are in words, it uses data types in symbols. So you have this symbol that's used instead of a data type. So instead of saying the word array, space, high temps, you get this, put a symbol in there, and then here's a variable, here's a symbol for a variable. So, and here's another symbol. So we're not gonna learn Perl in this class, but if you do learn Perl, just think it uses a lot of symbols instead of words for the data types. So let's see. I'm going to stop here at associative arrays and pick up the next video because we've already gone about halfway through this chapter. The next video will start with the concept of records. So this video will end, and part 2 will start with records and go to the end for that. But records kind of gets into some other concepts that I don't want to cover right now. So I hope you've enjoyed the video. This was the first part of chapter 6. Go ahead and start reading chapter 6. I'm not covering everything in the chapter, so it's not a bad idea to review the chapter. I will also go through the chapters before the final and tell you what it is you need to read specifically section by section, so that in my final exam reviews lecture that I will put together for you, And that will tell you what you should focus on in terms of the reading. But for right now, I would just start reading the chapter. I would say most of the chapter is relevant. So I would say cover to cover on chapter number 5, 6, 7 at least. 8, maybe not, but we'll get there. So hope you enjoyed the video, and have a good rest of the week.